This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on solving logarithmic equations. Our first example is log base 2 of 5x plus 1 equals 4. We start with the base, 2. The answer is an exponent, so 2 to the 4th power equals 5x plus 1. 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we get 16 is 5x plus 1. Subtracting 1 from both sides, we get 15 is 5x. And then dividing by 5, 15 divided by 5 is 3, and we get 3 is x. You've got to make sure that your answer leaves an argument of a function that's positive. 5 times 3 is 15, plus 1 is 16, so that's fine. If you plug in the number and the result here were negative, then that is not a solution, because a log function is only defined for positive numbers. 0 not acceptable, negative numbers not acceptable. Our next example is log 4x minus 7 equals 2. That's the common log. So we need to know the base of the common log is 10. Log base 10 of 4x minus 7 is 2. So we'll take 10 to the 2nd power is 4x minus 7. Starting at the base of the log, the answer is an exponent. 10 to the 2nd power is 4x minus 7. 10 to the 2nd power is 10 times 10, which of course is 100. 100 is 4x minus 7. Let's add 7 to both sides, so we get 107 is 4x. And then divide both sides by 4. 107 divided by 4 is 4x over 4. And the result, of course, is that x will be 107/4. Our next example is log base 3 of 81 equals 2x minus 3. So we've got to take 3 to the 2x minus 3. The answer is the exponent. 3 to the 2x minus 3 equals 81. This is now an exponential equation we have to solve. But 81 is 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. So 81 is 3 to the 4th power. So we get 3 to the 2x minus 3 equals 3 to the 4th power. If that is the case, 2x minus 3 equals 4. And then we're able to solve here, adding 3 to both sides. 2x is 7, divide by 2, and we of course get x is 7/2. And there's no issue there with arguments. 2 times 7/2 is 7, 7 minus 3 is 4. Log base 3 of 81 indeed is 4. Okay, our next example is log base 4 of x squared minus 6x minus 11 equals 2. So 4, the base, to the 2nd power, the answer is an exponent. 4 to the 2nd power equals x squared minus 6x minus 11. 4 to the 2nd power, of course, is 16, and we have a quadratic equation. But if we're going to solve an equation with an x squared, it has to equal 0. So we need to subtract 16 from both sides, so we get something equaling 0. 16 minus 16 here will be 0. Negative 11 minus 16 would be negative 27. So we'd have 0 equals x squared minus 6x minus 27. And this requires us to factor. That will be x minus 9 times x plus 3. And then we're going to set each one of those factors equal to 0. So x minus 9 is 0, or x plus 3 is 0. If x minus 9 is 0, x is 9. X plus 3 is 0, x is negative 3. But we need to check to make sure that we are within the domain. 9 squared is 81. 9 times 6 is 54. 81 minus 54 minus 11 is a positive number. That's okay. Negative 3 squared is 9. Negative 6 times negative 3 is 18. 9 and 18 is 27. Minus 11 is indeed 16. So both of those numbers are okay. When we plug those numbers in, we get 16. We don't have a negative number in the argument. That's something we need to take care of, because a log function is only defined at non-negative numbers. It's not defined at 0. It's not defined at negatives. The numbers must be positive after the log function. Our next example is 1/2 log base 5 of x equals 2 times log base 5 of 3. We're going to use the fact that we can pull the exponent up. So it'll be log 5, x to the 1/2 is log 5 3 squared. But what does x to the 1/2 mean? X to the 1/2 is the square root of x, and 3 squared is 9. So if log 5 of root x equals log 5 of 9, we know that square root of x must equal 9. And to solve for x, we're going to go ahead and square both sides. That can be dangerous. You could introduce extraneous roots, so it's a good idea to check that as well. When I square both sides, I get root x squared equals 9 squared. Root x squared is x. 9 squared is 81. So 81 to the 1/2 power is 9. 3 squared is 9. Indeed, that checks. Our next example is log 7 of x plus 5 plus log base 7 of x minus 1 equals log base 7 of 16. So how do we think of this? The sum of the logs, log 7 plus log 7 of x plus 1, is the log of the product. That would be log 7 of x plus 5 times x minus 1 would equal log 7 of 16. Multiplying those out, x squared 5x minus 1x, so that's x squared plus 4x minus 5, will equal 16. Why did I do that? Because it's both log 7. Log 7 of this equals log 7 of that. So this thing in brackets, x plus 5x minus 1, would have to equal 16 because they're both log 7 on each side. So now that we're here, we have a quadratic. The quadratic requires us to make it equal to 0. So I'm going to subtract 16 from both sides. As we do that, then we have 0 on the right side. 16 minus 16 is 0. X squared plus 4x minus 5 minus 16 would be x squared minus 21. X squared plus 4x minus 21. And then how do we factor that? That will be x plus 7 times x minus 3 equals 0. Now if that's the case, either x plus 7 is 0 or x minus 3 is 0. And to answer that question, we'll say that x is negative 7 or x is 3. But there's a problem. We need to plug these numbers into the very original equation. And if we plug negative 7 in, we have log 7 of negative 7 plus 5. That is a negative number. That is not permitted. Similarly, negative 7 minus 1 is negative 8. Can't have a log of a negative number there either. So negative 7 is not in the domain. Now how about 3? 3 plus 5 is 8. 3 minus 1 is 2. Those are both numbers that are positive. That's okay for a log function. So 3 is indeed our solution to that problem. Our next question is log 3 of x plus 1 minus log 3 of 2x plus 5 equals 2. We have to use our other rule of logs, namely the difference of the logs is the log of the quotient. So we're going to rewrite this as log 3 of x plus 1 over 2x plus 5 equals 2. So using that important rule, now we're going to use the other one starting at the base. 3 to the 2. 3 to the second power is going to equal x plus 1 over 2x plus 5. Starting with the base, the answer is an exponent. 3 to the 2 is x plus 1 over 2x plus 5. Now 3 squared is 9, so we'll rewrite it that way. And now we get to this challenging intermediate algebra question. How do we solve for x? I have a numerator and a denominator. This is a rational function. I'm going to multiply both sides by the denominator 2x plus 5 so that I will no longer have a fraction to work with. So multiply the left by 2x plus 5, multiply the right by 2x plus 5. On the left we're going to distribute. 2x times 9 is 18x. 5 times 9 is 45. On the right, 2x plus 5 in the numerator, 2x plus 5 in the denominator will divide out. So that's all that's left on the right side is x plus 1. So again, distributing 18x plus 45 on the left is going to equal x plus 1 on the right. We have to solve for x. So I have x's on both sides. I need all the x's on one side, all the numbers on the other. So I'm going to choose to get all the x's on the left side. So I'm going to subtract x from both sides to get the x's on the left side. But if that's the case, I'm also going to need to subtract 45 from both sides to get all the numbers on the right side. So subtract x on the left, subtract x on the right, subtract 45 on the left, subtract 45 on the right. The 45's go away, the x's go away. 18x minus 1x is 17x. 1 minus 45 is negative 44. And then how do we finish this? We divide both sides by 17, and we get x is negative 44 over 17. And that will conclude this lesson.